Hi everyone, in this presentation I'm going to discuss the impact of relativistic timescales, timestamping error, and reference frame transformation on the TDI, so time delay interferometry. This work has been performed within the Theory and Metrology group from CIRT, a lab of the Paris Observatory. So LISA will be measuring gravitational wave by exchanging laser beam between three spacecraft that will be orbiting the Sun, and to give an order of magnitude, a gravitational wave will cause a 10 to the minus 21 relative frequency variation between the three spacecraft. On the other hand, the laser that will be used for LISA are characterized by a noise at the level of 10 to the minus 13 in relative frequency variation. So there is an 8 order of magnitude difference between the noise and the signal that you are trying to extract, and we need to overcome this noise. The technique to overcome this noise is known as the time delay interferometry, TDI, which is a post-processing method that combines all the interferometric measurements by applying to them an appropriate delay to reduce the laser noise. So if we are denoted by SIG the interference between between two laser beams, so for example, if the laser beam from spacecraft 1 is sent to spacecraft 3 and interfere with the local laser from spacecraft 3 and we denote by S31, we'll have 6 such scientific measurements, and the main idea between the TDI algorithm is to produce some linear combination of these 6 interferometric measurements, which is written here. But on some of these interferometric measurements, we are applying to them some delay that are denoted here by capital L for arm length. It can be shown that, for example, this very particular TDI combination suppress exactly the laser noise if these capital L, so if the arm lengths are constant. TDI has then been extended to non-constant arm lengths to include clock noise and so on, and I think the state-of-the-art paper that is related to TDI is on archive and has been put on archive recently this year by Hartwig and Bailey. Nevertheless, all the TDI analysis that has been developed so far in the literature assume that there exists a universal Newtonian time and a universal notion of a distance. What do I mean by that? If I'm coming back to my X-TDI combination, you can see that here there appear time, which is a universal time, and on the other hand, this capital letter represents the interspacecraft distance, which is assumed to be universal as well. But of course, if you take into account relativity, it's very well known that each spacecraft will have its own local time, which is known as proper time, which will be different for the three spacecraft. And also the notion of a distance in general relativity depends directly on the choice of a specific reference frame. Even if you are forgetting about relativity, each spacecraft will have its own local USO for Ultra-Stable Oscillator, its own real clock, that will have its own behavior that will be characterized by a stochastic behavior or by some drift. So all the three spacecraft will have a different real clock. So to summarize, in LISA there will be 3 natural timescales. The first one is BaryCentric coordinate timescale, TCB, which is a timescale that is characteristic of everything that is happening on the solar system at the scale of the solar system. So it's a coordinate time, and it's useful to describe the motion of the spacecraft, the motion of the planet, and so on. It's also useful to describe the propagation of a light beam between the different spacecraft, and it's also very useful to describe the gravitational wave metric in the BaryCentric reference frame. So that's the first time scale. The next time scale is related to what's happening on the spacecraft, and it's a local proper time that will be delivered by an ideal clock on the spacecraft. This time scale is related to the TCB by some coordinate transformation which are dictated by general relativity. Finally, the third time scale is related to the time that will be delivered by a real clock on the spacecraft, and this one will be differing from the proper time because of the clock noise. So there will be drift and a stochastic part. And this user time scale will be useful because all the measurements on board will be timestamping with this time scale. Just to give you an idea of the order of magnitude of the various time scale, if you are comparing the proper time of the three spacecraft with respect to the coordinate time, TCB, you can see that there will be a very large drift, which is of the order of a couple of seconds over 5 years. This drift directly depends on the semi-major axis of the spacecraft, so it's very similar for the three spacecraft. And on top of that, you have some periodic variation you can see here that are different for the three spacecraft and that are of the order of the milliseconds. On the other hand, if you are taking some property for the clock noise, you can see that the user time will be different from the proper time, and there will be some drift here that is of the order of 400 seconds over 5 years. And then you can see that there will be some stochastic fluctuation of the clock time with respect to proper time, which is of the order of 10 to the minus 6 seconds. So you can see that relativity in clock noise can introduce large drift and large stochastic variation or periodic variation of various time scales. So how to take into account these various time scales in the LISA measurements? Well, first of all, the scientific measurements, which represent also the interferometric measurement between the various spacecraft, will be time tagged with respect to the user time, which is denoted by at tau here. On the other hand, there is another very important measurement that will be performed, which are the pseudo-ranges measurements, which are useful to construct the TDI variable. These pseudo-range measurements will be performed by generating a PRN code in every spacecraft, and the PRN code will be sent from spacecraft I to spacecraft J, and it will be compared locally with another copy of the PRN code so that it's possible to measure this quantity here, which is a difference between the receiving time of the signal minus the emitting time of the signal, all this time being expressed as user time. So this quantity RGI here, which has the pseudo ranges, include actually both information related to the clock desynchronization and the propagation time of the photon between the two spacecraft. So now the question is, how can we perform the TDI post-processing from L0 to L1 data, taking into account that there is various spacecraft, various time scales within LISA. So first of all, it's important to realize that there are 3 steps that are required to produce the L1 data in the BCRS reference frame. So BCRS stands for BaryCentric Reference System, which is a natural reference frame to perform gravitational wave searches or source parameter inference and so on. So first of all, what are the L0 data? A simplified version of the L0 data after filtering. Well, as I already mentioned, there will be some interferometric measurements, 6 of them, which are time tagged with respect to the local user time. And on the other hand, there will be some pseudo-ranges measurements here that are also time tagged with the local user time. On the other hand, what are we trying to produce as L1 data after post-processing? Well, we are trying to construct this TDI combination that are expressed as a function of the TCB, the coordinate time related to the BaryCentric reference frame. On the other hand, it will also be important to know the BCRS photon coordinate time of light, so basically this capital letter L, in order to produce the TDI. So it's important to realize that amongst all the steps that are required to go from the L0 to the L1 data, there are 3 steps that are required for sure. One of them is the clock synchronization, the other one is the transformation to the BCRS, and of course we need also to produce a TDI combination. One important point that we are trying to make here is that actually the order of the 3 operations can be chosen arbitrarily, and this is something that was a little bit unexpected. In particular, we have shown that it's possible to start straight from the TDI combination. So what I'm trying to make here, the point that I'm trying to make here is that the TDI can be performed before clock synchronization and before BCRS transformation. So how can we do that? Well, I'm coming back to the XTDI combination that was expressed here as a function of Newtonian quantity, so some universal time and some universal interspacecraft distance. And basically what we need to do is to replace this small t by the local user time, which is denoted by the at tau variable. On the other hand, the interspacecraft distance is directly replaced by the pseudo ranges measurements here. And if you do that, you can show that actually this quantity here, which depends only on L0 data or pure measurement, actually suppress totally the laser noise in case of constant pseudo ranges. So that's something that is completely new, and that was also demonstrated numerically using LISA node by Ultra-Stable and Jean-Baptiste Bailey. So the important point here is that it's possible to extend the TDI algorithm to use only the L0 raw data. So what are the advantages and disadvantages of proceeding using this method? Well, the main advantage is that you are using only the L0 raw data, so there is no pre-processing to do before you are applying the TDI. The main advantage is also that since you are not doing any clock synchronization and reference frame transformation, you're limiting the risk to propagate error through the TDI algorithm. But there are some disadvantages. First of all, it's important to realize that each TDI combination will depend on a different time scale. So here the X TDI combination will depend on the USO time from the spacecraft 1, but there will be other TDI combination that will depend on other USO time from spacecraft 2 and spacecraft 3. Also, we are losing the Newtonian interpretation of the TDI. In particular, the delay that you are applying here does not correspond at all to the distances anymore. They also correspond to, they also include contribution from the clock desynchronization. Finally, this variable, TDI variable, are intermediary variable that still need to be transformed into the BCRS. And there are some also points that you are currently explored. So this question needs still to be answered. So how hard is TDI variable sensitive to clock glitches and to large clock offset? That's a question that are currently open, and we are currently working on answering this question. On the other hand, it's possible to perform the TDI after clock synchronization or BCRS transformation. So that's the other extreme. So what you need to do in order to do that, you start from the raw data, so the interferometric measurements and the pseudo-ranges measurements that are all time-tagged with respect to the local USO time. You need to do some transformation here, clock synchronization and reference frame transformation, to express this quantity into the BCRS frame, and then you can use the standard Newtonian TDI expression where you replace the T by the coordinate time and the L are the photon coordinate time of light, and you can use this regular TDI algorithm. The advantage is that your TDI combination are directly expressed in the BCRS because you have transformed everything into the BCRS, and you preserve the Newton-like interpretation of your TDI. The disadvantage is that you need to do the clock synchronization and therefore frame transformation before, and so you will have error that will be propagating through the TDI algorithm. So just to summarize here, I have discussed two cases, one where you perform the TDI before the clock synchronization and the BCRS transformation, and one where I'm performing the TDI after. There are actually three cases, so let's come back to the three cases. You start here from the L0 raw data, again, a simplified version, which includes only the interferometric measurements and the pseudo-ranges measurements. You perform the TDI algorithm first, you get to this quantity that are still time-tagged with the local USO time, and then you still need to do the clock synchronization and the reference frame transformation to get to the L1 data, which includes the TDI variable expressed in BCRS and the coordinate time of flight of the photon between the various spacecraft. So that's the first case that I discussed 3 slides ago. The other extreme is when you perform the TDI after the clock synchronization and the reference frame transformation, so that's the other extreme. You start by synchronizing your clocks, and you express everything in terms of a common time scale that is denoted here by bar big tau, large tau. You do the reference frame transformation, so you express your measurements directly in the BCRS, so the interferometric measurements do not depend on the TCB, and you transform the pseudo-ranges measurements into coordinate time of flight of the photon, and then you can apply the TDI algorithm to get the answer that you want, the L1 data, which are the TDI variable expressed in the BCRS. And then there is a third way to perform all this analysis is to take here the middle road. So you do the clock synchronization, but you can perform the TDI algorithm here after the clock synchronization, and then perform the reference frame transformation. So it's kind of a compromise between the two methods. So the three approaches differ by the order of the operation, and they will be sensitive differently to all the sources of noise and errors. So that's very important because this represents the three various ways of doing your TDI algorithm when you combine it with the clock synchronization and the reference frame transformation to express everything in the BCRS. For the conclusion, well, relativity and clock noise introduce various timescales in LISA, and I've presented some order of magnitudes for these various timescales. They will impact the LISA-preprocessing, in particular the L0 to L1 preprocessing. And I've shown that there exists actually three different approaches to perform the TDI, the clock synchronization, and the BCRS transformation. And in particular, something very interesting is that it's possible to construct everything, all the TDI variable directly from the L0 raw data. So there is no need to do a preliminary clock synchronization. Although if you are doing this approach, you will have to resynchronize your clock afterwards to express everything in the BCRS. So which is the three approach between the three? It's a compromise between the way noise and the error propagate through the TDI, and it's a compromise between this and also the simplicity to understand the TDI algorithm and to keep this Newtonian interpretation of the TDI algorithm. So we are currently exploring these three approaches. Of course, the suggestion will be to use two different methods in LISA. Why? Because different methods are sensitive differently to the source of noise. So it can be interesting to implement two different methods as a cross-check in the real data analysis. So thank you for listening, and feel free to ask any question via the chat.